Today,
like 1 bedrooms are like 5K.
we're going to look at the vector dot products. So, does anyone here play a stringed instrument? Okay. What stringed instrument do you play?
Cello.
Cello, okay. My remarks will apply to a cello, even though I will not use a cello. Anyone here play piano?
Play 2 string.
Okay. So, you know that on a piano, down here somewhere, there's a pedal, right? The loud pedal, what they call it. You put your foot down on the loud pedal, and underneath the cover there are all these strings that have a damper on them. You put your foot on the loud pedal, it picks up, right? Yes, it does. Okay, what does that have to do with anything? Well, I want to digress for a minute. This is all going to have something to do with the dot product, I promise. So, you have like electronic equipment. You don't see this around very much anymore, but I guess there were people who had stereo systems, and it wasn't enough to have speakers and an amp and a record player and a tape deck. You needed this one more component that kind of looked like this. Anyone recognize from my diagram what this is? Equalizer, yeah. So what does an equalizer do? Well, it breaks up the frequency spectrum into groups, and then you can separately amplify them. If you've never seen one of these, you might think, how does that work? How does that work? I don't really know how it works, but it's an interesting idea. However, I know that if you get rid of these as quick as I can, because I don't have much time. I know that if you go over to a piano and you push the loud pedal and you hum real loud, the piano kind of hums back at you. It hums back at you at about that frequency you hummed at. Anybody ever done that? All right, after class, rush over to the music department and try it out. What's happening is you hum some of the strings which have the same frequency as you're humming at. They respond to it. They kind of vibrate. So they kind of detect that frequency. And if you make kind of a sound which is not just one frequency, like a lot of frequencies, like if you go to the thing and you go like that, you'll notice almost all the strings will start to vibrate a little, because they'll all pick up the frequency in your bang. What does that have to do with vectors and dot product and equalizers? Well, I'm not sure if we saw it in this class, but there was a video I thought I played where somebody explained that if you go in front of an orchestra with a mic and you kind of put that on like an oscilloscope, and you get some kind of weird pattern. You know, the sum of all the music. And this is just all these pure tones that are added together, different frequencies. So if you think of frequencies, the different frequencies as like being different vectors, or if you think of each of these strings being kind of a vector, then what I'm doing here with the piano is I'm breaking up the sound that I put into its component parts. And as we're going to find out, that's what the dot product does for us. Okay. Before that makes sense, I have a ways to go. So I better get started. So, what we're going to look at today is the dot product. If I have two vectors, v and u, which we're going to overuse today, we would write the dot product this way. That's the notation. What we're doing is we're finding a new way to combine two vectors. The output of the dot product is not a vector. It's a real number. It's just a number. So you want to keep in mind that whenever you see vector dot vector, you no longer have a vector. It's a number. In passing, there's another way to combine vectors that we're not going to look at. It's called the cross product, the output of which is a vector. Cross products only apply to 3D, 3 dimensions. We're really only looking at 2-dimensional vectors. And they're very important in physics. If you're a physics major, you'll run into them. But I'm not going to say any more about it, at least not today. Well, I'll just say one thing, which is unlike the dot product, the cross product is applicable only in very narrow circumstances, whereas the dot product, or its abstraction, is extremely it's ubiquitous. It's everywhere, and very important in a number of areas. Okay, so we're going to start off by defining how you would calculate a dot product. I have a vector v, which has components x1, y1, and a vector u has components x2, y2. Then I calculate v dot u as x1, x times x2, plus y1, y2, which is just a number. I'm going to note, and in passing, that were we to extend this, look at higher dimensional vectors, this pattern would persist. If we had a three-dimensional vector, we had z1 and z2 we add in. Okay. We want to, before we get to the good part here, we have to observe this operation, the dot product, and note a few of its properties. Some of them I'm going to demonstrate, some of them I'm just going to enumerate. The first one is that you can see right away that if I switch u and v, all I'm doing is switching x1 and x2, but multiplication is commutative, so I'm not going to change anything. That is to say, v dot u is equal to u dot v. That is, it's commutative. Similar to what we know about real numbers, if I take the sum of two vectors, I add u and v, and I dot it with w, well, I can distribute the w. This is going to be u dot w plus v dot w. And I can distribute it the other way, of course, too. I'm not going to go through this, but if you just give u, v, and w coordinates, calculate it out, you'll see that they're both the same. Right. You also want to note that if I multiply a vector times a constant, and then I dot it with another vector, well, what is that? C times v would be cx1, cx2, dotted with, x1, y1, dotted with x2, y2, would be what? That would be cx1, x2, plus c, y1, y2. That would just be c times x1, x2 plus y1, y2, or c times v dot u. So scalar multiplication is associative with respect to the dot product. Let's write that in here. C times v dot u equals c v dot u. And since we already saw v dot u is commutative, this is also going to equal v dot c times u. Okay, these are just a set of properties for the dot product that we're going to use. The last property has to do with what happens if you dot a vector with itself. Yes, I'll keep my notation here. This is x2, x2 plus y2, y2, no brackets, which is x2 squared plus y2 squared, which I'm going to write as the square root of x2 squared plus y2 squared squared. Take the square root and square it again, I'm back to where I was. But I write it this way because square root of x squared, x2 squared plus y2 squared with respect to u has a special meaning. It's the length of this vector, or its norm. So I can write this as v norm squared. Well, except to U. All right, let's put that down in our list here. U dot U is the norm of U squared. All right. So that's our little bag of tricks for the dot product. That's properties that we can count on using. Now we're gonna look at a really wonderful result you get. We're gonna find that the dot product can be used for another purpose other than just calculating some number. What we want to do, I think I'm running out of markers that work here. Take a look. Do I have another black marker? This works. I'm going to take this vector v and u, and I'm going to remind you of something we looked at on Friday, which is if you draw this parallelogram here, then one of the diagonals is their sum, but the other diagonal here is their difference. And actually, that's all I really want you to see, is that this diagonal here is the difference. And I want to mark this particular angle as theta for a particular reason. Right, now what we're going to do, we're going to have to work a little here. We're going to apply the law of cosines to this triangle. And we're going to get a rather remarkable and useful result. Okay, the way this works is, well, let's write down the law of cosine. C squared equals a squared plus b squared minus 2ab cosine theta. So my u minus v is going to be my side c, and it doesn't really matter which is a and b. So c squared, well, c is the length or the norm of u minus v, and I'm going to square it. A and d are norms of u and v squared minus norm of u, norm of v, 2 norm of u, norm of v cosine theta. Right, that's my starting point. Again, I have to do a little work here. I need to expand this, but I have a formula here that says that u minus v squared is just u minus v times dot u minus v. So let me work on this for a bit. U minus v dot u minus v. And then this property tells me that I can distribute over addition. Or subtraction. Right. So what does that get me? Well, u dot u minus u dot v minus v dot u, and then two minuses cancel, v dot v. Well, this is the norm of u squared. This is the norm of v squared. And this is minus 2. These commute, so it's just u dot v or v dot u. All right, well, that was the left side here. Let's write in the right side again. The norm of u squared plus the norm of v squared minus 2 norm of u, norm of v, cosine theta. Okay, now things get real easy. These u's cancel. These cancel. And I'm going to divide by minus 2. And that gets me the result I want. U dot v is the norm of u times the norm of v times the cosine of theta. I'm going to write that over here. This is a wonderfully important result. What it tells me is that if I have the components of u and v, right, I know how to find the dot product. So I know how to find the left side. But if I have the components, I also can find these norms. Well, that just leaves theta, which is to say, if I have the components, I can find the angle between these two vectors. Well, that's great. Let's look at an example of that. A real example. Let's say my u is 3, 5, and my v is 2, minus 8. So what does that look like? 1, 2, 3, 1, 2, 3, 4, 5. That's my u. V is 1, 2, minus 8. 1, 2, 3, 4, 5, 6, 7, 8. It's down here somewhere. And so this is going to tell me what this angle between them is. All right. Let's start with u dot v. U dot v is going to be 3 times 2 plus 5 times minus 8. So that's going to be 6 minus 40, or minus 34. That's the left side here. The norm of u times the norm of v times cosine theta. Well, the norm of u is square root of 3 squared plus 5 squared times the norm of v, which is 2 squared times minus 8 squared plus minus 8 squared, which is just 8 squared. So I have minus 34 equals, what does this add up to? 25 plus 9 is square root of 34. And this is 64 plus 4 is square root of 68 times the cosine of theta. Let me divide through. So I have the cosine of theta is minus 34. Square root of 34. I know square root of 68 is square root of 2 times the square root of 34. So 34, square root of 34, square root of 34, and 34 are going to cancel. This is just minus 1 over the square root of 2. What's the inverse cosine of minus 1 over the square root of 2? equation's over here, that's in the second quadrant, right, where the cosine is minus. And the cosine is 1 over the square root of 2. That's my side of my special angle, 45 degrees. So theta is 135 degrees. That's really good, right? We can do that now. I mean, we don't have to measure the angle. Maybe there's another way to do it. Maybe we could kind of measure the angle of U and then measure the angle of V, find the difference. But this is much more straightforward. All right, one more example that will demonstrate something a little different. Let's say U is the vector 2, 1, and V is the vector -1, 2. Again, let's take a look at what that looks like. 1, 2, 1. It's my U. And -1, 1, 2. So here. It's my V. All right, so let's start out with U dot V. That's -2 plus 2, that's 0. And that's the norm of this, which is square root of 5. The norm of this is square root of 5 times the cosine of theta. Well, that doesn't really change anything. We still have the cosine of theta equals 0. So where's the cosine of 0? Cosine of theta is 0. Need to know the cosine of, inverse cosine of 0. So right angle, the pi over 2 or 3 pi over 2. This is a very important result. It says when two vectors are perpendicular, their dot product is 0. So if I dot U and what we call U perpendicular, we get 0. You might want to look at these two as a pair here. When you dot two vectors who are parallel, it's just their product, the product of their lengths. But if they're perpendicular, it's 0. That turns out to be a really important feature. Okay. I need a break. I'm doing this all morning. All right. I haven't forgot about the piano. We're gonna get back to the piano in a little bit. In order to do that, we have to introduce a few more ideas. The next idea we want to look at is called a projection. So if I have some vector u here and a vector v here with some angle theta between them, I want to project v onto u. That is to say, I drop a perpendicular from the tip of v down to u. And at that point, now I have a vector here, which I'm going to call v projected onto u. All right, I want to think about what this vector is. I want to think about a way to represent it. So the first thing I want to note is that the length of my projected vector, its norm, is just the length of v times the cosine of theta. Right? This is a right angle here. The adjacent over the hypotenuse is the cosine of theta. So the length of the hypotenuse times cosine of theta is the length of this. I also want to note that the direction of the projection is in the same direction as u. So if I had a unit vector in the direction of u, I'm just going to call that u unit. That Vp onto u is equal to cosine theta u unit. This is just a vector in the u direction who just happens to have a norm of 1. Well, how do I create this? Does anyone recall how I can make a vector into a unit vector? I think we may have glanced upon that. I know that this is the norm of my vector u, that's its length. So if I multiply 1 over the norm times the vector, I'm going to get a unit vector, right? The length of this vector is, this is the length of this vector if I divide it by that length. Now it's a vector with length 1. Okay, so I can substitute here for my unit vector, vector u divided by the norm of u. All right, I'm almost done here. I'm going to do one more thing with my projected vector. I want to multiply, this is a fraction, I want to multiply the top and bottom by the norm of u. So on the bottom I'm going to get the norm of u squared. And times the vector u. And I noticed something. The norm of u times the norm of v times cosine theta, I have another name for that. Do you recall the other name I have for that? Anyone see the other name for that? Okay. This is just u dot v, a number over the norm of u squared times the cosine, no longer cosine theta, just times u, times u vector. Right? This is a number to that. Okay, let's put that down here. Projection of P onto U is U dot V over U squared minus U. Okay, this sounds like something that could be useful in and of itself. Let's look at an example. I have a vector U, 1, 4, and a vector V, which is minus 2, 1. I want to find the vector U projected onto V. So that's going to be 1, 4 dot minus 2, 1 over the norm of U. That's what? The square root of 4 plus 1 is 5 squared. And then times my vector U, 1, 4. Right? This is 1 times minus 2 plus 1 times 4, 5, or 2/5, 1, 4, or if I multiply this out, it's just 2/5, comma 8/5. No. Where did I go wrong? Oh, it's the wrong vector. Yeah, I'm projecting onto V, so I want the vector minus 2, 1. Okay. So that's minus 4/5, 2/5. I got my U and V mixed up. All right, let's at least take a look at what that looks like. I have a vector 1, 1, 2, 3, 4. That's my U. And my V is minus 2, 1. So I'm going to project this down here, and I'm going to get this vector minus 4/5 plus 2/5. So that's my projection vector. All right, that's nice and convenient. What if we do something a little more basic with this projection idea? Recall we defined 2 unit vectors yesterday, Friday. I equals 1, 0, and j equals 0, 1. What if we have some vector v, we'll say x1, y1, and what if I project v onto I and j? So v dot I is going to be x1, and v dot j is going to be y1. Well, that's just the components of v, right? In other words, we could express v as v dot I and v dot j. there's more here than it looks like. See, what this tells me is I have these two vectors. Recall that any vector, a vector u, can be expressed as a times I plus b times j, where a and b are some numbers. So every vector is just the sum of this, these products. This thing we call a linear combination. But also, given a vector, we can decompose it back into its components. We can decompose it back into its components. That's starting to sound like the piano, isn't it? As we have some kind of big sound that we, play near the piano, and then each of the little strings, they vibrate at their own frequency. It's kind of what we're doing here, except we're doing it with, pointing arrow vectors. I mean, what you have to imagine is instead of, we just have pointing arrow vectors with I and j, that we have a whole list of vectors, each representing frequency, and we can decompose it. Right. At this point, that's really all you really need to know about dot product. But I'm going to add a little more because I think it'll give you some kind of idea where this can go. I want you to think about I and j for a second. They're kind of connected with the x and y axis. We have two of them, right? We have a plane, we have two of them, and we need two. We couldn't create a vector just with one of them, but two is enough. Two is exactly the right number. And we call a set of such vectors, we have a name for it, it's called a basis. Basis is a set of vectors that you can use in a linear combination to make up all the other vectors that you might want to. But I and j are not the only vectors you could use. For example, if I had two vectors h and k, right? H equal to, say, 1, 1, and k equal 1, -1. All right, what does that look like? Well, here's h, here's k. That's a different set of vectors. It's also a basis, right? Because I could, anything I can make up as a sum of I and j, I can likewise, there's another set of values, we'll say c times h plus d times k. So you might say, well, okay, how can we find these components c and d? We can find them the same way that we found them with I and j. We can use the dot product. So c is going to be equal to b dot h. It's not quite true. See here, I and j have a norm of 1, so we we have to normalize this. We have to divide by the length of h. And d, of course, would be v dot k divided by the norm of k. All right, I just have a few more things I wanted to say about this. To go from this basis to this basis, we're kind of just changing the coordinate system, right? You use the word just as if it's not a big deal. We call that a linear transformation. We've talked about linear transformations in a different way. We talked about graphs where we move them around, or we squeeze them, or compress them, or reflect them. But now we're talking about it in a very general way. We're talking about changing the basis that we describe a vector in, and that's a big subject. You may have heard of a class, linear algebra. You may have heard that we do a lot with matrices in this class. Well, a matrix is just the representation of a linear transformation. And that's what that class is really about, is the study of these linear transformations. So that's obviously way past this class. Those of you who are interested in computer science will definitely want to take this class. I think I've already mentioned this physics application with a piano, where instead of having a kind of a pointing arrow vector, we have a frequency, or the frequencies as a vector. In computer science, we have a much more straightforward application. Everybody sits in front of a computer screen, and maybe you're looking at something 3D, right? Often your computer, you have some model for some world. I don't know, you have some trees. I'm not going to draw stick figures, they always look awful. But you have some 3D world, and what do you need to do? You need to project it onto a two-dimensional screen. That's exactly the same use of the term projection I used earlier. But in addition, before you project it, the user might want to move around in that 3D world, right? So what are you doing? You're doing some kind of linear transformation. Maybe you're rotating this, maybe you're moving it closer to the screen, moving it further away. These are all linear transformations. Now, the computer, it has to do that transformation. Every point on this is some kind of pixel on your screen. So your screen has thousands of pixels. You might imagine that's a lot of work. That is a lot of work. It's so much work that we don't even let your computer do this. Those of you who've kind of taken a computer apart, you might have seen, sometimes there'll be a video card, right? A cable will hook up to your terminal and plug into the computer here. And it used to be that all the video card did was you could set a pixel on the screen. But nowadays, video cards will come with a little engine on them, and you'll tell the card, well, I have this 3D representation, and I want to rotate it, I want to do a transformation, and he'll do all the computer work for you. Even your, whatever, your 3 gigahertz Pentium processor is not fast enough to do all this work. We just have special hardware just to do it. The last thing I'll say is, you may have heard, if you're doing computer work, you may have heard of something called DirectX. That's for Windows or more generally OpenGL. These are interfaces that let you talk to this graphic screen in a very uniform way. So, this is not the only application for this stuff either. So, okay, that's all I wanted to say today. I hope you'll bring in questions on Wednesday so we can answer questions instead of